last video we talked about collision model and that atoms need to collide in order to react. But not every collision leads to a reaction. There's two things that need to happen for a collision to actually result in a reaction. One of them is that they have to collide with the right orientation. And the other factor is that they have to collide with enough energy to make that reaction happen. And that minimum amount of energy is referred to as the activation energy. Now, when looking at those two factors, it's activation energy that is more important. So, the definition for activation energy is what I just kind of described. It's a minimum amount of energy that is needed in order for molecules to react. It's supplied by the kinetic energy of the molecules. So the molecules have to be moving fast enough at a high enough temperature to have enough kinetic energy to get that amount of energy to be at that minimum amount. Now, the activation energy for one reaction is different than it is for another reaction. So it's very reaction specific. And when you have a reaction occur, there is a moment where sort of everything kind of compiles together and we have what is called an activated complex or a transition state of your reaction. So we're going to look at an example for this. And we're going to just use a generic reaction. A plus B makes C plus D. And if you look at that reaction and you make a graph of the energy versus the reaction pathway, what you're going to find, now we're going to assume that this is an exothermic reaction. We're going to put the reactants at some energy, A plus B. Now, if we assume that it is exothermic, that means this reaction will release energy, and the products, C and D, will have a lower energy than the reactants. Okay? Now, what we are saying is in order for A plus B to turn into C plus D, we have to give it some minimum amount of energy. We have to get it to a point where then it will automatically react. Now, if we look at some things going on in this reaction, the amount of energy we gave this, okay, so from the reactants to the top of this peak is called the activation energy. We give that a symbol E sub A. The amount of energy that is the difference between the reactants and the products is either known as delta E, or sometimes, if we assume that it's constant pressure, we'll say that it's delta H. Okay? You guys know that in an exothermic reaction, delta H is negative. In an endothermic reaction, delta H is positive. You've already learned all of those things. Okay, so this should look somewhat familiar to you, but the new piece that occurs is right up here, right at the top. This is for where we form either what we call the activated complex, or some people will say transition state. You can read more about this in the book, but essentially, this is just an unstable intermediate kind of portion, something temporary between the reactants and the products, and it does not appear in our balanced reaction. Okay. Now, this reaction that I've shown you is exothermic because the amount of energy given off, if you think of this amount would be the final amount of energy. This amount up here would be your initial amount of energy. And final minus initial would give you a negative value. Okay. So on your pages in your note packet, you'll see this diagram. Okay. That if you have reactants starting at a higher energy, products ending at a lower energy, that implies that it's exothermic. The E sub A is always measured from the reactants to the tip of the curve. So from here to here. This height difference is the activation energy. So, what if it's endothermic? Well, if you flip over your page to the next part of the note packet, you can see that if it's endothermic, the reactants start with a lower energy, the products finish with a higher energy, but we always measure our activation energy from the reactants energy to the tip of the curve. So now you have a much greater force to overcome. Now, I'm going to go back a picture. I want you to think of this for a second. Think of it like a ball rolling down a hill. If I have a ball sitting on this level right here, I have to give it a minimum amount of energy to get it up the hill. But once it reaches the top of the hill, it's going to roll kind of on its own. Okay? So the activation energy is relatively low. But in an endothermic reaction, to get this to go up the hill, I'm going to have to give it a lot more energy. So its activation energy is higher. And once it reaches here, it'll convert to the products on its own. Okay? So that's another way of thinking of it. Now, the delta E, or the delta H, has no effect on the rate of the reaction. But we do know that the lower the activation energy, the faster the rate of reaction. And we also know that if one direction of a reaction, like if we looked at A plus B makes C plus D, if we know that releases energy, and we would call that exothermic, then we would know that the reverse reaction, C plus D, would have to add energy to it in order to get the reaction to turn into A plus B. And we would call that one endothermic. And you learned that back in chapter 5. You know that if one reaction in one direction is exothermic, it is endothermic in the reverse reaction. Now, the last thing we need to talk about in this video is something called a Maxwell-Boltzmann distribution. And in this one, I've seen this asked a lot on IB exams, so it's good to know what this is. But looking at this, it's basically talking about a number of molecules versus the energy. So think of the area under the curve as a number of molecules that could or could not react. Now, if you think of the molecules in this and under this portion of the curve, this is a large portion of the molecules. These molecules would not react, and I want to add, you should think about why they would not react. Okay? Now, if you come up with the right answer in your head, hopefully you realize it's because they have an energy that is less than the E sub A. So even though they might bump into each other, they're not going to bump into each other with enough energy for the reaction to work. Okay, so the only molecules that are reacting are the ones that are going to have at least an energy equal to or greater than the activation energy. Now, this first curve, we're going to call this T1. We're going to say that this is occurring at one temperature. But what would happen if I raised the temperature? Well, we all know that if we raise the temperature, the molecules are going to start moving faster. When they move faster, they have a higher chance of colliding. And because they're moving faster, they'll probably have more molecules that will actually have that activation energy. So I'm going to draw a second curve underneath, or on this graph here. Now keep in mind that the fraction of molecules total can't change. So if I'm going to change and say more of them react at a higher temperature, okay, notice now I have a higher fraction of molecules that have the E sub A that matters. But I had to lower the peak of the curve because I had to spread out the distribution. This is often asked on an IB exam. So they're looking for two things. Number one, they want to see that you actually can show me that you have a greater fraction of molecules that have E sub A or higher. Okay, so we've done that. The second thing they want to see is, did you know that the peak has to shift in order to make the molecules under the curve stay relatively constant? I mean, this, I'm not perfect at drawing these, but the area under the curve has not changed. So we all know that at a higher temperature, you get a greater fraction of molecules to react because they have a kinetic energy that is at least equal to, if not greater than, the activation energy. And remember, when it comes to orientation and activation energy, the activation energy is more important. You still have to have the right orientation, but the activation energy is more important. Molecules can collide in the right orientation, but if they do not have enough energy, they will not react. Okay, so that brings us to the end of the videos that you guys have to watch for this unit for now.